the differential dy, this is our formula, dy equals f prime of x dx, that just pretty much comes from the derivative. So we have the derivative defined to be dy dx, and we recognize that all we have to do pretty much is just move the dx over. And that's just going to be our formula here. And then recall that dy, what does dy represent? So dy represents the amount that the tangent line is rising or falling. All right, based off of your center and dx. How far are you away from the center? All right, that determines the value of dy. All right, so we went through a couple of examples computing dy, and then we went into what can we use these for. And so one application of that would be to estimate the value of a function using the differential. And this is where we left off, right? We were just kind of went over this part. Is that correct? We didn't do any estimating, right? You wrote some stuff down?
We just we started going over
that part. Okay. So this is what you should have on your paper already?
Yes.
But the idea here is what we want to do is let's say we know the value of f of a. So is there a way to use that value to estimate the value of the function for an x that's near a? So we have a value of the function that's near, or the value of x that's near this value. Can we use the known value to estimate this other value, function at this other value, this value here, I guess? So can I estimate, and a plus dx is this one up here, right? And what we said was that as long as dx is small, as long as I'm close to a, that dy, which is your rise of the tangent line, is going to be pretty close to delta y. Delta y was the rise of the true difference in y, right? So dy was the true difference of these values. So if we're close, dy is pretty much delta y. If we're far, it's not, right? We can see clearly it's not the same. And why am I mentioning delta y? Well, going back to our computation, we said that delta y was equal to the difference in those y values, right? F of a plus dx minus f of a. So that's what those were. So delta y is the difference between these. And f of a plus dx was equal to f of a plus delta y. And so if I add delta y to f of a, that will give me f of a plus dx. So that's this part. And then we just said that if x is near, if dx is relatively small, that delta dy will be approximately delta y. So this value that I want to find can be found using this computation, f of a plus dy. All right, so let's see on the next page. We want to use differentials to approximate the cosine of 29 degrees. And at some point, because I'm using differentials, oops. So we're going to be using this formula. So we want to be able to see this. This is approximately f of a plus dy. First, do you see that cosine? We want to approximate the cosine of 29 degrees. So 30, because cosine 30 is something that we know, right? Cosine of 30 degrees. So 30. But this actually, what I was going to say is that this needs to be equal to the original. Cosine of 29 is cosine of 30 minus 1 degree. I can also think of that as the cosine of 30 plus a negative 1 degree. That way. And so now do you see that this is kind of what this says over here, right? So when I write it this way, do you see that a must be 30, right? And the small change, the dx, must be negative 0.1 or negative 1 degree. Now, dx is a distance. So it doesn't make sense. Dx is a real number and so is a. So right now, 30 degrees is not a real number and neither is 1 degree. So what we should do first is probably convert those to real numbers, radians, yeah. So we need to convert both of these to radians. Right, because both a and dx should be a real number. Well, 30 degrees we know is pi over 6. Well, that's the radian measure, right? Plus, what's negative 1 degree? So I know that one way to do it would say that I know that pi is equivalent, or other way around. I know 180 degrees is equivalent to pi, right, in radians? So therefore, 1 degree will be pi over 180. So this will be a negative pi over 180. So according to differentials, the formula in blue, cosine of pi over 6 plus negative pi over 180 should be approximately f of a. F is the cosine function, right? So it should be approximately cosine of pi over 6 plus dy. What's dy? So dy is that formula, right, that we wrote down. Dy is f prime of x dx. So if f of x equals cosine x, f prime of x is going to be negative sine x dx. So with x equaling, that's our a value, x is a, with x equaling pi over 6 and dx equaling negative pi over 180, then dy here is going to be negative sine of pi over 6 times negative pi over 180. If we compute that, we know the sine of pi over 6 is 1/2. So that's negative 1/2 times negative pi over 180. That's going to be positive pi over 360. So now I have all I need to approximate. So going back to my problem here, the cosine of pi over 6 is root 3 over 2 plus this pi over 360. If I really wanted to, I could probably get a pretty close approximation without a calculator. I know that root 3 is approximately like 1.5-ish, and I know that if I divide that by 2, that's like 0.75. If I really wanted to, I can take pi, 3.14, maybe grab a couple more decimals, divide that by 360, get a decimal there, and then add those two decimals together, right, those two numbers. So my point is it can be done without a calculator if we really wanted to at this point. But let's just use our calculator for now, just for the approximation. So what is the actual approximation here? So root 3 over 2, was I right about that? It's like 0.75-ish? I don't know. Could be wrong. I was off by quite a bit. Okay. So root. So I'm going to put that all as all together in one line there. Plus pi over 360. So you said 0.87? So that's approximately, where's the cursor? 0.875. If I round it.